Can I mute it when I don't use it?
Yes, you can turn it off.
Like this. Okay.
But you start now.
Ready? Okay, hello everyone. Today, unexpectedly, it's me chairing the seminar because Magda is away and asked me to take over. So today we are happy to host Terra Blevins for her talk. And Terra has recently graduated with PhD from University of Washington when we were happy to meet last year. So she was supervised by Luke Zettelmeyer. She's currently doing postdoc at University of Vienna, and next year joining faculty at Northeastern University in Boston, right?
Yeah.
She has been working, among others, on multilingual language models, multilingual data, and her excellent work did great contributions to development of language technologies to making them available for speakers of diverse languages throughout the globe.
Okay, awesome.
Yeah.
Thank you
Sure.
for the introduction, Tomas. So I'm very excited to be here today to tell you about my work on multilingual language models and how we can improve their performance for all languages. So as the title of this talk suggests, I'm going to be focusing on the language technologies of large language models. And these models have become very hot, very popular in NLP recently. And many of us have probably either worked with them or used them ourselves through chatbots like ChatGPT. But the reason these models are so popular is because they're really powerful. And so they have improved performance on many different NLP tasks and brought access to these tasks into the mainstream beyond just for NLP practitioners. But the way these models learn to do this is by being trained on very, very large amounts of text data. So since we started training language models for this purpose, the amount of data used to pre-train them has increased by many orders of magnitude, up to 15 trillion tokens seen by the Llama 3 model released by Meta AI last spring. But usually when we talk about data distributions and data trained at this scale, we're mainly thinking about primarily English data. In terms of other languages, we usually actually have a lot less data available to train these models. So if we look at an open source multilingual text corpus like MC4, you can see that languages like Czech or Swahili have a lot less data available to them on the internet than a language like English. And this plot is actually a little bit misleading because I plot it on a log scale. In terms of absolute values, the data distribution looks more like this. So obviously English has much more data available to it than any other language. And as we move away from the few highest resource languages, which are mostly Western European or Chinese and Russian, the vast majority of the world's languages fall in this long tail of the overall data distribution. And actually, because of the way MC4 was created, that only covers 100 languages that were the highest resource languages in the web crawl, and then they discarded any other languages in the data. But there are obviously many more than 100 languages in the world, right? So if we want to incorporate more of these languages into our language technologies, especially the ones backed by pre-training, we're going to have less text data available in order to do so. So because of these data limitations, the de facto modeling setting for most of the world's languages is to use a multilingual language model. And luckily, the way we train multilingual language models is pretty straightforward. So we can take the setup we would use to train a monolingual model on a language like English. And then we can just switch out the text data so that we have a multilingual text corpus instead of a monolingual one. And so even though we don't need any architectural or other training objective changes, the model will learn to model all of these languages that are seen in the training corpus. And so this gives us some really useful skills in the multilingual model. First of all, it learns to model many languages, and we can also pool training signal across closely related languages. So this helps make up for some of those data limitations we saw earlier. And the model also learns some really useful cross-lingual capabilities just from being trained on each of these languages simultaneously, even though there's no explicit cross-lingual objective in the pre-training setup. And actually, because the only change we need to make is the training data, this means that in practice, all large language models trained these days are multilingual. That's because in order to get enough data to train these large-scale models, they are basically trained on the entirety of the internet with some minor data quality filtering. And so since the internet contains many different languages, not just English, these models see all of these languages during pre-training. And so what this means is we can have a chatbot like ChatGPT perform the same task for us in many different languages. So here I've asked ChatGPT to write a news article for me about discovering unicorns living in the Andes Mountains, and ChatGPT will do just that. They'll give us a pretty fleshed out news article that's fairly long and discusses all of the points we raised in the instruction. If we translate this instruction into German, we get a very similar response from the model. It's formatted similarly, and it covers most of the same topics that the English article did. We can also interact with the model in much more obscure languages like Latin, and it'll respond in Latin, but we start to see some differences in the model's output. So first of all, we only get a paragraph back from ChatGPT. And in this instance, the model's response is discussing the things we asked for in the prompt, but it's not completing the task we asked it to. So this paragraph isn't the start of an article that we asked for. And the model also starts to make some mistakes here, that we don't see in other languages. So here ChatGPT says, you should know that my language is English, and I do not understand idioms other than Latin very well, right? So this is a logical inconsistency in the model's output. And we don't see this sort of inconsistency in high resource languages like English. So what this means is that even though large language models are multilingual, they don't benefit all language speakers equally. And I can show you this anecdotally with outputs from ChatGPT, but we can also see this by evaluating our models on multilingual benchmarks. And so here we're looking at ChatGPT's performance on natural language inference and question answering. And of course, as we move away from performance on English to performance in other languages, accuracy of the model immediately drops off. And for some of these languages in the benchmark, which generally correspond to those languages in the long tail of the data distribution we saw earlier, accuracy approaches or even is at 0%. And so besides just the data limitations of these models, another reason this happens is due to something called the curse of multilinguality. So to explain how this works, let's say we were able to train a model on just one language, like English. That would mean that the model would be able to allocate all of its parameters to encoding some information about that language or the information in its training set. But when we train a multilingual model, this is no longer the case, right? Instead, the model has to divide up its parameter space in order to encode each of the languages that it's trained on. And so this means the model effectively has fewer parameters to capture each of the individual languages it's trained on than a monolingual model of the same size. And this is borne out by the model's performance on a language when compared to a monolingual model for that same language. So here we're comparing GPT-J's performance on these benchmarks versus Bloom's, where GPT-J is a primarily English model and Bloom is an explicitly multilingual one. And as you can see, Bloom underperforms GPT-J on all of these English tasks. And so the curse of multilinguality is a very well documented phenomenon in multilingual models. It generally occurs in massively multilingual models that are trained on dozens or up to 100 languages that are quite diverse from each other. And there's generally a stronger effect of this curse on low resource languages in a language model's training setting. And so this is because these languages have less training signal and so end up being underrepresented in the model. And work has found that increasing the size of the model can reduce the effect of the curse of multilinguality because you have more parameters available to capture these languages. But this isn't a feasible solution in the long term for scaling language models. So this is because if we want the skills we see in something like OpenAI models on English for other languages, OpenAI models have hundreds of billions of parameters in order to have those skills in English. So naively scaling a hundred of billions of parameters model to even 10 languages isn't feasible in most hardware settings. So today I'm going to talk about my research on the curse of multilinguality and how we can break this curse in multilingual settings. So I'll talk about when language models learn to be multilingual and see how we can see the curse of multilinguality develop during the pre-training process. And then I'll talk about two modeling directions we've looked at recently for trying to mitigate this curse. Okay, and so first I'm going to talk about when language models learn to be multilingual. So this is work from our EMLP paper on analyzing the mono and cross-lingual pre-training dynamics of language models, done in collaboration with some of my colleagues at the University of Washington. And the question we're trying to answer here is, when do language models become multilingual, or how do they go from being randomly initialized and trained on a pretty simple training objective, right? Just trying to predict the next word in the training example, to having these complex multilingual and cross-lingual skills, such as translation or cross-lingual transfer. And of course, during this process is also acquiring the curse of multilinguality that ends up affecting the final model. And so if we can see how this develops during the pre-training process, maybe we can better diagnose it and develop ways to intervene in this effect. So the way we're going to test these models for knowledge is use a probing setup. And so to probe the model, what we do is we take the language model we're interested in and we freeze it so that its weights and representations remain fixed during this process. And then we take some text that we're interested in and we extract representations from the model encoding that text and train a second machine learning classifier to recover some linguistic feature from the representation. So here you could use any machine learning classifier, but we use a linear projection layer, just mapping from the model's representation space to predicting the label space of the task. And we look at a number of different linguistic features that the model learns during pre-training, but for simplicity in this talk, I'm going to focus on part of speech tagging. And so usually when we probe a model, we take a fully trained language model that's been released and we test it for the knowledge that it learned. But we want to know what happens throughout training, not just at the end of the training process. And so what we do is we retrain X-ELMR from scratch and we keep different checkpoints of the model from different stages during training. And so by doing this, we essentially have snapshots of what the model knows at different points in the training process. And we can probe these independently to build a trajectory of how the model's knowledge changes over time. And so we can use these trajectories to answer some really interesting questions about multilingual pre-training dynamics. So for instance, we can ask, when do models learn each of the languages that they're trained on? And so this plot is showing the training time of X-ELMR on the x-axis and the performance on part of speech tagging for these probes on the y-axis. And here, each of the points on the plot represent the step where the model first acquires 98% of its overall best accuracy for that task. And so this is essentially telling us when is the earliest point in the training process that the model has acquired the vast majority of the knowledge it's going to acquire about that task. And as you can see from this plot, even though we're zoomed in on the first 10% of the training process for X-ELMR, it learns most of these languages that we're looking at very early on in training, at least for part of speech tagging. And if we zoom out to the full training scale, you can see that some languages like Korean are learned slightly later, but still pretty early on compared to the full 1.5 million training steps of X-ELMR. We can also ask, what do language models do with this information once they acquire it? So here, for these languages, we see that the model's knowledge remains relatively stable after acquiring it very early in training, but this isn't always the case. So for some languages, like Japanese, we can see that the model has much larger fluctuations in knowledge throughout pre-training. And while Japanese mostly recovers by the end of the training process, this isn't always the case. So for some languages, we find that with these fluctuations, there's actually a general downward trend with the model essentially forgetting information over time. And so this is evidence of, for instance, the curse of multilinguality developing as these languages are outcompeted and pushed out of the model's representation space. We can also ask, when do language models learn to transfer information between languages? So here we're using the same probing setup I described earlier, but now we are training the probe on one language and then using it to recover features in a different language. So in this example, we're training the probe using English, part of speech tagging data, And then we're applying that English probe to see whether it can recover French part of speech tags, or essentially seeing how well aligned these linguistic features are within the model. And so we see a couple of differences here in the cross-lingual setting than what we saw in the monolingual one. So unsurprisingly, performance of probing across languages is, in absolute terms, generally worse than in language. This is borne out by other cross-lingual transfer experiments and multilingual models. But we also find that transferring, in this case from English, into these different languages is generally acquired later than performance in either of the individual languages, particularly, for instance, for Japanese. And we also find that this cross-lingual knowledge and alignment isn't symmetrical. So for instance, we see that transferring into English from Arabic versus transferring into Arabic from English are learned at different times. And even though English into Arabic is acquired slightly later, it performs better overall throughout the training process. And for instance, in the case of English into Swedish and vice versa, they're acquired at roughly the same time and perform similarly, but then they diverge, with English remaining stable and Swedish degrading. And so for clarity in these plots, I focus on some languages that show us the overall trends we see throughout the pre-training process. But if you take a step back and look at the learning landscape for all of the languages we have evaluation data for, you can see that multilingual pre-training processes are very noisy, right? So there aren't any consistent trends that are held for all of the languages that the model is trained on. And this is a specifically unique thing to multilingual modeling. If we look at similar experiments done for Roberta on English, you can see that for part of speech tagging and many other linguistic features, the knowledge is acquired and then held relatively stable in the model. So you don't see these large fluctuations that we do in the multilingual setting. And of course, we also see that the model will forget information about some of these languages due to the curse of multilinguality. So as the model has to stochastically optimize essentially all of these languages throughout training, the knowledge for each individual language can fluctuate. And for some languages, this means that the final checkpoint of the model isn't a good representation of what the model can potentially learn about that language from the training data, because for many of these languages, there's an earlier checkpoint that performed much better. Okay, so this is a demonstration of how the curse of multilinguality develops during pre-training, focusing on X-ELMR. And now I'm going to talk about two directions for how we can mitigate this curse in different multilingual settings. So I'm first going to talk about how we can reduce it in one setting with targeted multilingual training. Okay. So the curse of multilinguality generally develops in a massively multilingual setting where the model is trained on many different diverse languages. But a recent trend in multilingual modeling has been to train targeted language models that are focused on a single language family rather than 100 different languages. And so this has been found to work really well by mitigating competition between diverse languages, instead training on languages that are more synergistic. And so in this work on targeted multilingual adaptation for low resource language families, we essentially perform targeted training for the Uralic language family and as a case study, and then try and find best practices for doing this in the future. And so with this case study, we look at the entirety of the modeling pipeline from data collection to applying the model on downstream tasks. And we look at different potential hyperparameter settings and other design choices, and then see how they affect the overall outcome of the model. And so the first thing we look at is performing data collection for the Uralic language family. And so this figure shows the geographical range of the Uralic language family, which is mostly spoken in Northern Europe and parts of Russia. And as you can probably see from these language branch names and maybe the languages in the legend, many of these languages are pretty not well known and uncommon. And many of them are actually endangered languages. And so because of this, we need to do careful data curation to try and add some more of these low resource languages into our data set. So because for most of the languages that we end up training on, they're actually not in popular multilingual corpora like CC100 or MC4. And so after doing our data survey, we end up using data from the Opus parallel text corpus, the Oscar massively multilingual web crawl, and in cases where we have this data for the language Bible text corpus. And as you can see from this data distribution plot, there is a very big difference in the amount of data we have for some of these languages versus others. So for instance, the languages in the top part of the table have much more data available to them than all the languages in the bottom part. And so for the purposes of this training setting, we consider the top languages to be high resource and the others to be low resource. And astute viewers may have noticed that we include Russian in this data corpus, even though Russian is a Slavic language, not Uralic. And that's because the 3 high resource Uralic languages we have are all written with a Latin script. But many of the low resource Uralic languages are actually written with Cyrillic and they occur in parts of Russia or the former Soviet Union. And so they have a lot of contact with Russian. So even though Russian isn't in this language family, we include it to facilitate learning and transfer to these low resource languages. And so once we have our data, we next need to decide what model we're going to train on this language family. And so in this setting, we're actually looking at adapting an existing model, X-ELMR, to this data. And so X-ELMR is a massively multilingual masked language model. And so it's already been trained on the high resource languages that we're going to adapt the model to. But it hasn't seen any of the low resource languages that we want to incorporate into the model. And so because of this, we also perform vocabulary specialization to try and improve the model's tokenization and embeddings for the language family in general, but particularly for these low resource languages. And then once we have our specialized model, we perform language adaptive pre-training to adapt X-ELMR to the Uralic language family. And so language adaptive pre-training is a common adaptation setup where you continue training the model on its original pre-training objective, but with new data in order to specialize it. And we consider a number of different design choices here. So we consider different vocabulary sizes for our specialized vocabulary, as well as the number of training steps or the amount of adaptation time we use to specialize the model. And we also consider some different random seeds to see what noise this introduces into the model. And finally, we consider different values of the language sampling alpha, which is how we control how much we up or down weight low resource languages. So a language sampling alpha of 0 would sample from all the languages equally, regardless of the amount of data we have for that language. And a language sampling alpha of 1 would just sample from the data distribution directly. And so first we validate our approach to see if it outperforms baselines on this Uralic language family data. And so in the few shot setting, we find that our best adaptation approach works the best for all of these languages. So it's using a training setup of 400K training steps. So that's the largest training setup we consider, with a language sampling alpha of 1 and the largest vocabulary we consider. Yes. Yeah, so that's the language sampling alpha. What? It's basically a temperature sampling. Yeah, so you can see these trade-offs here. Yeah, it's that temperature sampling alpha. Okay, and this one setting works the best for all the languages in the few-shot dependency parsing setting. We also evaluate performance in a zero-shot dependency parsing setting. So these are our lower resource languages that have evaluation data available and universal dependencies, but don't have any training data. And so to fine-tune the model for these languages, we task fine-tune on the most closely related neighbor that does have training data available. And so in this setting, we have much more mixed results. For most of these zero-shot languages, adapting the model and specializing the vocabulary does improve performance, but there isn't a consistent trend with the size of the vocabulary. And we also have this one outlier with Skolt Sami, where we find that using the original tokenizer actually performs best, and then continue to train the model on the Uralic language family. And so we perform a more careful analysis of this in the paper, and we find this is actually an artifact of our data collection process, where the data we collected for Sami overrepresents North Sami, which is a different language actually, but gets grouped with Skolt Sami. Okay, so this is great because we validated that performing targeted training improves performance for the Uralic language family, but we're also interested in what the best way to do this is so that we can have better insights moving forward in this setting. So we also perform a statistical analysis of these training factors we considered to see what effect they have on the downstream model. So here, we're looking at the effect of each individual parameter and averaging across the other ones in each setting. And we also perform a regression analysis using a linear mixed effects model in order to see which parameters have a significant effect and what size the effect is. So there are a lot more details about the analysis in the paper, but here I'm going to use it to indicate which factors end up being significant on the downstream model. And so, for instance, we find that the number of language adaptive pre-training steps has a significant effect on all of these languages. And that's not surprising. Training the model for longer better specializes it to that language. We also find a significant effect in terms of the size of the specialized vocabulary. We're using a larger specialized vocabulary improves performance on these languages. But in terms of the language sampling alpha, we actually find that it's only significant for 2 of the languages in the few-shot dependency parsing setting. And so these languages specifically are Erzya and North Sami, which are the only 2 low-resource languages in our data that we have few-shot dependency parsing data for. So this is essentially telling us that the language sampling alpha is, in this setting at least, only significant for the low-resource languages and doesn't have a significant effect on the high resource ones. And we see some similar results in the zero-shot dependency parsing setting. So again, training for longer improves performance. And in this case, the language sampling alpha is significant for all of these languages because they're all low resource. But we find that the size of the specialized vocabulary isn't significant here, which we also saw in the original zero-shot dependency parsing results. Okay, so to summarize some of these best practices we found, we find that data curation is crucial for improving performance on these low resource languages. And this is actually can be more difficult than one might think, as we saw with the issues we have with Skolt Sami. So we recommend working on language families you're either very familiar with or consulting a domain expert to make sure that the data curation is going effectively. We also find that specializing the vocabulary to that language family improves performance, but it also makes the model much more efficient because as you do vocabulary specialization, you can reduce the overall size of the model by having a smaller vocabulary. And so this efficiency point is really important because one of the largest effects we find is that training the model for as long as possible on your new data setting is really helpful for improving performance. So by reducing the size of the model, you can train for longer in a given compute budget. And finally, we find that in the targeted multilingual setting, using a low sampling alpha over the languages significantly benefits low resource languages without harming the high resource ones. So this is a bit different from what's been found in the massively multilingual setting, where there's a pretty consistent trade-off between high and low resource languages with the language sampling alpha. But in this setting where the languages are related, this doesn't seem to be the case. And so we recommend using a aggressively low sampling alpha in targeted multilingual settings to benefit the low resource languages you're training on. Okay, and so from this previous section, we see that targeted multilingual training can have a lot of really useful benefits depending on your desired setting, right? So it reduces the curse of multilinguality for all of the languages in this family. And by benefiting performance for all of them. And this comes from training on related languages and being able to pool data across similar languages and reduce interlanguage competition between diverse ones because you're no longer training on those diverse languages. But obviously, there's some drawbacks here, right? So the scope of the model is much more narrow than a massively multilingual one because now you're only training on a single language family. And so because of this, you also lose some of the cross-lingual abilities that we've come to expect from multilingual models because you can no longer transfer information across this language family boundary. And so ideally, we'd like to design a modeling approach that gives us the best of both of these, right? So being able to pool information effectively for related languages, but still keep the cross-lingual benefits of massively multilingual training. And so in this last section, we're going to propose a new way to do language modeling that does just that. And so this is our work on breaking the curse of multilinguality with cross-lingual expert language models. This was done in collaboration with a number of great researchers at the University of Washington and Tomas from here at Charles University. And this paper is going to be an EMNLP next month. Okay, and so the approach we're proposing here is going to be in contrast to basically the standard way of doing language modeling that I've already described, where you have a model with all of the parameters you've allocated to your system and is trained on your full set of multilingual data. And moving forward, I'm going to call this dense language modeling. So what we propose instead are cross-lingual expert language models, or X-ELMs, where instead of learning a single model for all of your languages, we train a set of expert language models that together as a full set learn the entirety of the scope of massively multilingual modeling. Okay, and so this is building on some prior work into how we can build more efficient and scalable training methods for large language models. And they do this by looking at the different training regimes for these modeling settings. So if you look at how we would train a dense model that I just described, this training setup becomes very expensive as you scale the size of the model. And that's because the model's parameters need to be synchronized. So as you need to split the model across more GPUs in order to do model parallel or data parallel, you incur both additional hardware costs because you need more GPUs to train that model, but also computational costs because you need to communicate between the different GPUs during training. And so one approach that's been proposed for more efficient language modeling is mixture of experts training. But you still have a lot of the same drawbacks in this setting. So for instance, even though some of the parameters in a mixture of expert are independent, each of the experts are, you still have shared parameters within the model, which means the model still needs to be synchronized and trained all at once with the full set of GPUs. So what they do is they take the philosophy of mixture of experts even further and make the experts completely independent. So now there are no shared parameters that need to be synchronized across experts. And so because of this, you no longer have communication costs, and it actually reduces the hardware costs as well, because in a setting where, for instance, you only have one GPU, you can train each of these experts sequentially rather than in parallel. And so they use this to train modular expert language models for different English language domains. But this is very similar to what we wanted for different languages. And so we take this and we apply it to training expert language models for different language families, where now each expert is specialized to a given language family or set of related languages, but you still have this full set over the entire multilingual space. And so since each of the experts are specialized to some amount of the multilingual space, how we choose to allocate this data to these experts is really important. And so we consider two approaches for data allocation. The first is to do typological clustering over the languages we're going to train on. So this is pretty similar to the targeted language modeling setting we looked at earlier, but now instead of using language families in order to cluster the data, we use some syntactic properties about the languages to build a similarity matrix, and then use that similarity matrix to build a balanced hierarchical clustering over all of the languages we train on. So for these experiments with X-ELMs, we're using these 16 relatively high resource languages in MC4, and then we can build this tree over all the languages based on the syntactic similarity. Once we have this tree, you can pick the number of experts that you want to train on these languages and find the nodes in the tree that give you that number of clusters. And then in this clustering setting, every language that is the child of the same node is assigned to the same expert and used to train it. And as an alternative, we also consider using TF-IDF clustering over the training documents. So this is a data-driven discovery approach for clustering the data, and it doesn't use any explicit linguistic features like the typological setting does. Instead, it only uses the implicit features that just appear in the text of each of the documents. So this was used in prior work on branch train merge for clustering data. And so we include it as a data-driven baseline to see whether using explicit linguistic features are helpful in the multilingual setting. And so once we've chosen how to allocate our data, we then specialize the experts using branch train merge. So the way we train these models is we first branch from a seed model and use that seed model to initialize each of our experts. So at the beginning of this training process, the experts are all copies of the same multilingual language model. And in this case, we use X-ELM as our initialization. But this step of branching from a seed model is really important because having a shared initialization means that the language models are in the same optimization space during the specialization training. And so they're more effective to ensemble for inference. And then once we have these experts, we then, yes.
You said they start from the same seed. You mean they start from like initial like random seed, or they have a shared, or they have like a pre-trained model as a base?
They have a pre-trained model as a base. So we use X-ELM here as the initialization. And so maybe I don't think I explained this clearly. So having this burn-in period where the model has already been trained on some amount of data that's somewhat in the setting you're adapting to is really important because of the like non-convex optimization space of the models. Having the shared burn-in where they're already going to the same local minimum is really important for keeping them in the same space when adapting on different data settings. Does that kind of make sense?
Yeah.
Okay. And so once we have these experts, we then specialize them to their data in the cluster that's been assigned to them and merge the specialized experts into an X-ELM set that we can then use for multilingual inference. Okay, and again, there's a few different ways you can use these models for inference. So if you have some information about your evaluation setting, like maybe the language it's in, you can choose the expert that will perform best on that setting and use it as an independent language model. But you can also ensemble these experts to pool information in settings where you either don't know what's going to perform best or have like a multilingual setting. So for ensembling, you can run the example through each of the experts and then get a shared probability distribution from the experts by performing a weighted average over each expert's probability distribution. And we get this weighted average using this alpha that measures the similarity of the evaluation example context to each of the experts' underlying data distribution. So the data distribution that was used to train that expert. And so the first thing we consider is choosing what the optimal number of experts is for this data setting with 16 languages and data taken from MC4. And so here the x-axis is looking at the number of experts, where k equals 1 for the number of experts, it's actually doing language adaptive pre-training in the dense language modeling setting because you only have one expert in that case. And k equals 16 in the typological clustering setting is equivalent to having monolingual experts, or one expert for each language that we train on. And so overall, we find that typological clustering performs better than TF-IDF clustering over all of these languages, though we see some exceptions. So for instance, English actually performs better in the k equals 4 TF-IDF setting. And this is likely because English just has much more data available to it than all of the other languages. And so it can train on more data in that setting. And we find that Swahili actually performs best in the monolingual setting where it's given its own expert. And this is likely because Swahili is pretty unrelated to any of the other languages we train on. It's a Niger-Congo language, and it's the only language from that family or Africa that the X-ELMs are trained on. And so then once we find our best setting, which for the rest of these experiments is going to be that typological clustering setting at k equals 8, we find that using X-ELMs improves performance over all of our dense baselines. So here we're comparing to X-ELM, which is the original seed model used to initialize each of the experts. And the dense model is that K equals 1 setting we saw where you continue training but one expert on all of the data. And so here I want to point out that we're using a fixed computational budget. So for every expert setting, regardless of the number of experts, we have the same amount of data and training steps that is allocated to that full set. So in the setting where you train 8 experts, each expert is trained for 1/8 of the compute that the dense expert is. But we still find that using X-ELMs improves performance, and it does so for all the languages we consider. So here we're looking at the delta improvements over the seed model and the dense baseline. And in the case of every language, it improves over both. And we also find that this setting doesn't over-benefit the high resource languages. Actually, regardless of the amount of data we have for the languages, they generally benefit, and we actually find a slight negative correlation where lower resource languages might be more benefited. And then we also look at downstream tasks to see if these perplexity improvements correspond to in-context learning improvements. And so we're looking at 2 metrics here. Accuracy is the average accuracy of the model on that task across all the evaluation languages. And then win rate is the number of languages that that model performs the best on for a given task. And so generally the results are somewhat more mixed here than we find for perplexity. So we do find that generally the X-ELMs improve performance over the dense baselines. And we find in the case of XMLI that actually ensembling the experts performs best, showing that we do get some useful cross-lingual knowledge in relevant application settings. Okay, so finally, we also look at how we can perform language adaptation in the X-ELM setting. So multi-round training or doing another round of branch train merge actually works really well for specializing the model to new languages. So let's say we have some new data that we want to adapt to. We can then branch and initialize a new expert, but this time we initialize from one of the experts we already trained rather than the seed language model. We then continue training our new expert on the data we want to adapt to, and once it's specialized, merge that expert back into the X-ELM set. So this is a pretty efficient way to do language adaptation because you only need to train one new expert in order to incorporate the language into the set. And also, we don't have the risk of catastrophic forgetting that you see with some other language adaptation approaches because none of the existing experts are altered during this process. We just add the new one. And so similar to the other settings, we find that this gives us good performance gains over the dense baseline. So here, the dense baseline would be to do language adaptive pre-training, building from the dense baseline we trained earlier. And instead, we find that branching from an expert that has been trained on a more typologically similar language to the new language improves performance. And this is particularly true in cases of languages that are pretty distinct from the overall data distribution of the original X-ELM set. So for instance, we look at adapting to Azerbaijani, which is a Turkic language. And so we find that branching from the expert that's already specialized to Turkish and continued training reduces perplexity by over half. Okay. And so from all of these experiments, we find that X-ELMs reduce the curse of multilinguality using the branch train merge paradigm, right? So this allows us to scale multilingual modeling parameters very efficiently in terms of computation, while also allowing us to explicitly allocate those parameters to different groups of the languages. And so we no longer have this interlanguage competition across cluster boundaries. And so this gives us better performance, but it also gives us easier adaptation and training in general of the multilingual model. And because the training is more efficient and more flexible, it's able to be used in low compute settings where maybe you have less hardware available. Okay, so in this talk, we've talked about when language models learn to be multilingual and how this correlates to them developing the curse of multilinguality during the pre-training process. We then looked at 2 different approaches to multilingual modeling and how we can reduce the effect of the curse of multilinguality in both of these settings. And so we argue that these 2 modeling approaches, targeted and X-ELM for massively multilingual, are key to reducing the curse of multilinguality in the long term. And so we find that by training targeted multilingual models, we're able to reduce the curse of multilinguality within a single language family by pooling information and improving performance for the high and low resource languages in that setting. Okay, and so we then extend these insights into the massively multilingual setting using X-ELMs. So now each expert is a targeted multilingual language model trained on related languages. But because we use the branch tree merge paradigm, they're trained in a way that they can still be used in tandem for massively multilingual modeling. And they're also very adaptable to new settings as needed, giving us many benefits for low resource and low compute settings, such as the communities that speak these languages. Okay, so I'd like to just thank my collaborators one more time, and I'm happy to take any questions.
Thank you very much for a great talk, Terra. Are there any questions from the room?
Yeah, thanks. Nice. So, so for example, one simple question. So I assume in the final mixture of the experts, so these are like uniform weighted, or would there be an option to like weight different of the experts differently so that some of them are like more important in the mixture?
It kind of depends on what you, so if you mean in the inference setting, like in this one? Yeah, so there is weighting.
So that's the alpha, or which one?
Yeah, so the alpha is how we up or down weight the probability distribution. And that depends on how similar the evaluation data is to the data used to train that expert. So if it's very similar to the data, likely that probability distribution is going to be better.
Oh yeah, nice. I missed it.
Yeah.
Thanks.
Thanks for the talk. I have one question, which I'm not sure if you have an answer for, but when I see ensembling of models like this, my natural question is, what about tokenization? Because if I wanted a language model for a language family, I would probably use a different tokenizer than for another language family. And this way necessary, some languages must be over-segmented. Do you have some ideas how to do such ensembling even over different vocabularies, or what was it even an issue for you?
So it wasn't really an issue in most of these settings. So for the 16 languages we considered, X-ELM was already trained on that. So the tokenizer was, I mean, it probably wasn't optimal for those languages, but they were at least considered when the tokenizer was trained. It could have been more of an issue for the language adaptation experiments, so we didn't look super carefully at that. But yeah, so I don't think it was an issue, at least in these 16 languages, not in particular, though in general, the tokenization issue is a big deal, right? And Tomas and I have talked about this. Yeah, because that's an interesting problem, right? Doing this ensembling would be a lot more difficult with a different probability distribution. I think there has been some work on this for ensembling models trained independently, but I would need to take a closer look to see if they'd be feasible in this setting. I do think another promising direction is byte level modeling, right? So where you would still have the same vocabulary, but maybe it would better represent all the languages because it's at the byte level or some better version of the byte level. Yeah.
Thank you.
Yep.
Is this on? Okay, thanks. Yeah. So earlier you had ways of clustering languages. I think you had the LangTvet clustering and the TF-IDF clustering. I was just kind of curious, what is the base for the TF-IDF clustering? Is it shared vocabulary or shared?
Yeah, so it's basically going to be shared vocabulary, right?
Okay.
So I don't have this slide anymore, but we do look at the the language distribution in both of the clustering settings, where the typological clustering, it's going to be, hard allocations of the languages to each of the clusters. And for the TF-IDF clustering, it's still pretty sparse because, right, like you're clustering based on essentially vocabulary in the TF-IDF setting. But you do get some mixing with the idea of like, if you had some documents that have maybe more English text or like because it has terminology to a specific domain, you might still get grouping across languages.
Yeah. Okay, thanks.
Okay. Have you tried distilling the ensemble?
Distilling. Do you mean like averaging?
Into a single menu. Well, distilling based on some data and possibly also averaging, although I guess that would result in lower performance.
Yes.
But maybe if the original models were already larger. And the second question: how many experts did you have in the experiments? Like,
so we looked at experts from like 1 to 16, but for most of the experts we used 8. Most of the experiments we used 8 experts. That's just because that's what we found performed best.
meaning that like the alpha, you force like the lowest 8 values out of the 16 to be exactly 0, so that
No, so in most settings we only had 8 experts.
Okay.
So we didn't have 1 expert per language. I mean, we considered that, but it was actually kind of a surprising finding was that grouping languages, even though they weren't necessarily super closely related, worked better than having independent experts per language. But I mean, we do look at, so there's a couple of questions there. We do look at sparsifying the ensemble. So for instance, only keeping the top 4 rather than the full 8. And that works pretty well. It doesn't really reduce performance by that much. And we also looked at not distilling the models, so that would be really interesting, but doing the model averaging that I mentioned. And so we actually found that doesn't work super well, which was kind of surprising because it did work really well in the English setting that we're kind of basing this work on. So my hypothesis, and this is something I'm working on now actually, is that this is just due to the data distributions being more different when you train on different languages versus different data distributions. And so I'm thinking about ways we can keep the models better aligned during training so that you can do stuff like model averaging.
Thank you.
Yeah.
Are there any questions from Zoom? No questions. Okay, maybe I have one more in topic of expert language models. So nowadays we can also have dense models which are instruct tuned.
Yes.
And that's like, I think also general questions like for all the research doing adaptations for new languages. So how do you think like adapting to new languages can face with this instruction tuning of like base model? Is it possible, for instance, maybe with expert models to somehow preserve those instructions, or maybe it's like better to use the base model and then instruct it afterwards?
Yeah. I mean, I think that's definitely an open question. I think there has been some work on like task expert models that's kind of related to, but not like actually associated with branch train merge, where you can train expert models for different tasks and then like use the model averaging or ensembling to like pair information, like kind of compositionally pair information for different tasks. So I think you could kind of build on that and maybe have like an expert that's specialized to just instruction tuning, for instance, maybe with English, maybe for, different experts for different languages that you have instruction tuning data for, and then try and do some ensembling like this, but only over the subset of the experts that you think are relevant, like the instruction tuning one, the English one, and the target language one, for instance. I think that would be really interesting.
Great, thank you.
So, I have one more question. Thanks for a nice talk, first of all. If I understand correctly and summarize it in one sentence, you're essentially trying to pack all the languages that wouldn't fit because of the curse of dimensionality into a single model. But have you also considered like the universality of the knowledge, so that you'll be trying to suck out the information across the languages and evaluate cross-lingually? So that's the question. So not just putting more languages into the mix, or having separate experts for separate language families and then running them concurrently, but seeing how much they learn together, learn from other languages.
You mean like coming up, maybe.
So if you, as an extreme example, you could have one data set which is for English, and that would be on math topics, and then you would have a data set which would be on chemistry topics, and that would be only in Czech or German.
Yeah.
And you would like the model to be able to predict also good knowledge in chemistry in English, although it has seen the knowledge only in the other language.
Yeah. Okay. So I think the question is kind of on transfer of information cross-lingually based on.
I would not call it transfer because it interferes with the term of transfer learning, but yes,
Sure.
it is.
Yeah. But yeah, so I think that's an open question, even in like the dense multilingual models where you train like one, like, right, because I don't think it's super well known because of the distribution of the pre-training data, what the model is actually learning in language versus acquiring from a different language and then somehow mapping it into that language. But I think that kind of builds on the question Tomas had for like experts for things other than just language, right? Like instruction tuning in that case, but you could also have experts where some are for languages, but some are for a specific domain if you know that all of your data is in that domain, right? So having a math expert in that case. And I think that would maybe be an easier way to control for that. So then you can see if the expert that's trained on all of your math data, if you remove it, like how does the model perform? And if you add it, are the ensemble able to interface essentially with that expert and learn from it? Is that kind of? Yeah. I mean, I think generally we have thought about like ways of clustering across languages that are more domain specific, like cross-lingual mapping of the data. But we haven't come up with any feasible ideas for doing that. So, I mean, we're always open to it.
Yeah, thanks.
Any other questions from the room or Zoom? Okay, thank you, Terra, once again for great talk, and thank you, the audience, for great questions. Yeah, that's everything for today. Next week, I'm not sure. Okay, next week is the Indra and Honza Haj will have their talk. I don't remember the topic, but you basically will be assistant for like it's like maybe you can say it. Okay.